Hello guys, welcome on Tesla Adventures. In this video, we are starting heat transfer by radiation mode, and we will discuss some basic things about this mode of heat transfer. So first of all, in this mode of heat transfer, you can see that the heat is being transferred by the use of by the means of electromagnetic waves. And the best example of this mode of heat transfer is the transfer of heat from sun to earth. We know that sunlight travels from sun to earth, and it carries the heat of sun to earth. So this is the heat transfer by radiation. You must have seen in the microwave oven the food which is being kept for cooking is also cooked by the means of microwaves. So that is also a part of electromagnetic spectrum. So in microwave oven, heat is also being transferred by the means of radiation. Now, as the electromagnetic wave do not require any medium to propagate, therefore this mode of heat transfer is also suitable for vacuum mediums, which means that we can transfer the heat through vacuum through heat transfer by radiations. Now, this is the fastest mode of heat transfer because we know that in this mode of heat transfer, the electromagnetic radiations moves with the speed of light. So this is the fastest mode of heat transfer among all three modes. Now, this also does not require any medium to propagate, and if medium is present, then it will also propagate through that medium, but it does not necessarily require any medium to propagate. And also we know that when electromagnetic waves are traveling through any medium, they do not heat up the medium. In fact, they heat up the surface on which they are absorbed or they are incident. We know that when the sunlight is coming from sun to earth surface, then it does not heat up the air. So you must be wondering that why air is hotter then, because it is due to the fact that air which is in contact with earth's surface is hotter as compared to the air which is away from the earth's surface, because the electromagnetic waves which are coming from sun are incident on earth's surface and they are absorbed in earth, due to which earth's surface gets heated, and the air which is in contact with that heated earth surface becomes hotter. But electromagnetic wave does not heats up the air. And it is very basic thing that each matter, whether it is living or non-living, it emits some of the electromagnetic radiations, and its temperature should be greater than 0 Kelvin. So we know that each matter has temperature greater than 0 Kelvin, as 0 Kelvin is not achieved yet. So each matter, whether it is living or non-living, emits some electromagnetic radiations, and our body is the best example of this fact, that we know that our body also emits some electromagnetic radiations, and therefore when we sleep and when we cover up our body with the blanket, then the radiations which are emitted by our body are trapped inside that blanket, or the heat is trapped inside the blanket. So the body is also a radiator. Now, to explain the heat transfer by radiations, a scientist Prevost presented a theory or some points on basis of which this can be explained or this can be understood. So the first important point was the fact that all bodies radiate some thermal radiations. Obviously, the body should have the temperature greater than 0 Kelvin, which is obviously which is obviously of all the bodies, which all the bodies have the temperature greater than 0 Kelvin. Now, the amount of heat radiated by a body is also dependent upon the nature of the radiating body, that how is that body in terms of radiations, and how good a radiator is that body, and the area of exposure, which is the area through which that body is releasing the radiations. Greater is the area, and greater would be the radiations emitted, and the temperature of the body. We know that when we are feeling a high temperature, when we are feeling sickness, then we also feel that our body is radiating some radiations, and some other person standing near us can also feel the heat radiated by our body. So when we are having some high temperatures, then our radiation power emitted by the body is increased by a significant amount. Now, each body also absorbs some part of the radiations emitted by the surroundings, which means that if I am sitting in a room, then all the things which are situated near me are radiating some energy, some radiations, and my body is also absorbing some of them. Okay, so my body is a radiator as well as my body is also a absorber. Now, the rate, if obviously if the rate of emission of my body is greater than the rate at which it is absorbing the radiations, then its temperature would decrease, obviously, because it is radiating much more energy than it is absorbing. And if it is vice versa, true, that if my body is absorbing more than it is radiating, then I can say that the temperature of my body will increase. Now, obviously, if the rate of radiation, at the rate at which my body is radiating the energy, or the rate at which my body is absorbing the energy are equal, then the temperature of my body will become steady. It will become constant, and it will become equal to the surrounding temperatures. now, I can say that what is the ideal black body? So, ideal black body is a hypothetical or conceptual visualization of such a body which absorbs all the possible radiations which are incident on it. So, we can say that ideal black body is a hypothetical body, conceptual body, which can absorb all the possible radiations which are incident on it. Sorry. Now, the ideal black body, this is a very strange fact that each ideal black body is also ideal emitter of that radiations, which means that we can say that sun is an ideal black body because sun is also a ideal emitter or radiator of the electromagnetic radiations. So sun is also ideal black body, and we will prove this fact that each body which is a good radiator of any radiations is also a good absorber of those radiations. Obviously, the radiation process and absorbing process are occurring at different temperatures. Now, there is no such naturally occurring body which is 100% ideal black body on Earth. Obviously, sun is 100% ideal black body, but a lamp black and a platinum black material are good approximation of ideal black bodies. And the concept of ideal black body was developed by Ferry. We'll come on ideal black body again in upcoming topic, Kirchhoff laws. So I'm giving the basic definition of ideal black body and idea of ideal black body in this video. Now there are some important definitions which are useful later on. So let us discuss those definitions in this video. So first of all, this is absorptive power. It is the radiation energy absorbed by a body divided by total radiation energy incident on it, which means that if we are making some radiation to incident on some surface, and 50% of those radiations are absorbed by that surface, so we can say that the absorptive power of that surface will be 0.5. Okay. Now similarly, reflective power is the amount of radiation energy which is reflected by a body upon the total amount of radiation energy which is incident on it. You must carefully notice the fact, or the word which is I'm using here is reflected, not radiated. Okay, radiation is a different process. If a body is radiating the energy, it is radiating its internal energy, and reflecting is a different process. If some radiations are incident on a body, then it can reflect some part of that radiations. Okay, so we are concerned about reflection here. Transmission power is also the radiation energy transmitted by a body upon total radiation energy incident on it. Okay, now emissive power is something else. Now emissive power of a body is the total radiation energy emitted by a body per unit area per unit time. Or we can say that the energy radiated by a body per unit time is emissive, is obviously radiated power, and emissive power is radiated power upon area. So emissive power is numerically equal to intensity, you can see, and emissivity is something else. Emissivity is a dimensionless, unitless constant E, which is the ratio of emissive power of any body at temperature T to the emissive power of ideal black body at the same temperature. This ratio is called as E. So let's suppose that if some body has a emissive power of half, emissivity of half, E is equal to half, then it means that if that body is at the same temperature as compared to an ideal black body, then that the emissive power of that body is just half to the emissive power of the ideal black body, which is at same temperature. So obviously we know that ideal black bodies are the perfect emitter also, radiator also. So the reference is used as ideal black body here. So maximum possible value of emissivity can be 1 for an ideal black body. Okay, now let us discuss the Stefan-Boltzmann law. So we all know that each body which has a temperature greater than 0 Kelvin radiates some of the energy, whether it is living body or a non-living body. So Stefan and Boltzmann developed a numerical analysis about the power radiated by a body at temperature T. So according to them, the power radiated by a body is directly proportional to the area through which that body is radiating the power or energy, emissivity of that body, and to the fourth power of the absolute temperature. So the final formula is sigma EA T to the power 4, where sigma is a proportionality constant, which is also called as Stefan-Boltzmann constant. Its value is 5.67 into 10 raised to power minus 8. Okay, so we know that the power emitted by a body is dependent on the temperature of the body itself. So power emitted, I can write down that power emitted by a body is sigma E A T to the power 4, where T is the temperature of the body, and the power absorbed by the same body is sigma A T naught to the power 4, where A is the absorptive power of this body and T naught is the surrounding temperature. It is very important to note that the emitted power is dependent on the temperature of the body, while the power absorbed by that body is dependent on the temperature of surroundings. Okay, so if the emitted power is greater than the absorbed power, then the temperature of the body falls. Obviously, body is emitting more power, and if this emitted power is less than the absorbed power, then the temperature of the body rises. Okay, and if these are equal, then temperature remains constant. Now let us assume that there is a body which is initially at a higher temperature as compared to the surroundings. So obviously the emitted power will be more, and the net power emitted will be, I can write it down as dq by dt. The net power emitted will be equal to the power emitted by a body minus power absorbed. Okay, now as we know that the body is emitting the radiations, so its temperature will start to fall because it is emitting its internal energy, and its temperature will start to fall, and a time will come when its temperature will become equal to the temperature of the surroundings. And at that time the power emitted and power absorbed will become equal, and the rate at which it is emitting the power at that time will be equal to the rate at which it is absorbing the power at that time. So we know that if T will become equal to T naught, let's suppose at infinite time, then dq by dt, net power exchanged, will be 0, and therefore sigma EA T to the power 4 will be equal to sigma AA T to the power 4. I have used this relation as T is equal to T naught. So you can see that these constants E and A are equal, and we also know that E and A, E is the emissivity and A is the absorptive power or absorptivity. These are constant for a body. These are some constants which remain always constant for a body. They do not depend on temperature. So if they are equal at this temperature, then they would be equal at all other temperatures. So in any numerical analysis, you can take E and A numerically equal. Okay, so this was all in this video, and in next video we will be discussing Newton's law of cooling and its graphical analysis and numericals dependent on it. Thank you.